applications of the natural exponential growth of decay model. So the first examples will be cases where we're given the equation, and then we'll do a set of examples where we have to find the equation. All right, so whenever you hear something that's compounded continuously, that means exponential growth in terms of money. All right, so the principal amount, P, which would be the initial amount at time 0, that's what the initial, so this would be the initial amount at time 0. Right, the account is paying. The annual interest rate, expressed as a decimal, is the compounding continuously. And so our interest rate would be the percent at which the money grows. That's that K value, right? That's what R is. R is K. It's just in terms of monetary, so we use interest rate, but it means the same thing, right? If your money grows by 4.5% per year, meaning you're gaining 4.5% on whatever your money was over the year, right? So if it's $100, over the year you gain $4.50, right? That's what the interest is. You gain that percent. And so that is the K value. That's the percent at which it's growing. All right, and again, we always put percents in as decimals, so we write it as a decimals. All right, so my compounded continuously equation is A, which represents the future amount, T, which represents the time, P is my initial value, and R is my percent. All right, so the principal on an IRA, so P is 100. The interest rate R, which is 12%, and I write it as a decimal, would be 0.12. Again, that would be the K value. It grows by 12% over the years, right? 12% per year over the years. T equals 45, and then you just plug numbers in. So how much money will there be? Well, you plug in our values into that equation. And make sure you're careful with the exponent. Make sure you put parentheses around the multiplication between your 12% and your 45 years, right? So make sure that's all up there in the exponent. And then I usually just round it to dollar amount, so I usually round dollar amounts to the penny. So it comes out 221,406.42. So it grows by quite a lot. Again, it's growing by quite a lot because 12% is a pretty high percent, and it's for a very long period of time. Alright, so again, it's growing by a significant amount of money. Alright, so there's the first example. That's how much money we have. Alright, second example, alright, which apparently my equations were really small. Alright, normal healing wound can be modeled by an exponential function if A naught represents the original area of the wound. So again, suppose you measure it and that's the original area of the wound. And they actually do this in the hospitals now. It's a little more scientific than this, but they do sort of pay attention to wounds, especially if they think it might be infected. Alright, so look at the area of the wound, and the wound should be decreasing, right? Your body should be healing. And we kind of know how the body should heal at a certain rate, right? If you're a healthy individual, wounds should heal at a fairly significant or constant rate. Alright, so the equation A gives me the new area after a certain amount of days have passed. Alright, how much the body has healed, so the area should now be smaller, should be shrunk. Alright, it's given by the equation A naught e raised to the negative 0.35n. And so just in case you want to know what that 0.35 represents, a 35% decrease in the wound size over days, each day. All right, that's what that 35 means. That 35 is telling me every day my body should reduce the size of the wound by 35%. It's exponential healing, so to speak. All right, so suppose that a wound initially had an area of 100 square centimeters. If healing takes place following this model, how large should the area of the wound be after 3 days? And so we know our initial amount, so A naught is 100. We know our time is 3, so 100 e raised to the negative 0.35 times 3, and then you plug it in. And I'll probably just round a couple of decimal places. Actually, it comes out 34.99377. So I'll probably just round to the whole number in that case. 30. So it reduced by a lot. It was at 100 square centimeters. It's now down to 34 square centimeters. So it went from 100 to... So it decreased by quite a lot over those 3 days. Because every day it's moving down by 35% of whatever it was. So day 1 it decreased by 35%. Day 2 it decreased by 35%. Day 3 it decreased by 35%. And it puts us at about 34 centimeters. So the body is doing its job. Right, the second part of this question, how large should it be after 10 days? Alright, so now we're looking for 10 days later. And so same equation. 100 e raised to, I don't know why I put a parentheses there. E raised to the parentheses, negative 0.35 times 10. Again, make sure you're careful that that's all up there. And I'm going to guess this should be a pretty small number. Alright, and it is. It's reduced down to 3 centimeters squared. So I start at 100, so it's fairly insignificant at this part. Very, very small after 10 days. Next example. Alright, E. coli is a type of bacteria that inhabits the intestine of animals. Bacteria is capable of rapid growth. That's why you always have to be careful if you get it with your eggs and things. Bacteria is capable of rapid growth and can be dangerous to humans, especially children. One study, the E. coli bacteria is found to be capable of doubling every 49.5 minutes. Alright, and so you could model this one slightly different than what we did. You could use a base 2. We're going to use the exponential growth, which they gave us. Suppose the number n, which is the number of bacteria, E. coli bacteria, after t minutes is modeled by the equation n of t, where n naught is the amount of the initial bacteria. The growth rate is 0.014 t, and so remember, that really means it grows by 1.4% growth in minutes. Time isn't minutes. Every minute. Alright, that's pretty fast. It grows by almost 1.5% of its size every minute. So first minute it grows by that second minute. So that's a fairly fast growth rate. Alright, find the number of bacteria per minute after 99 minutes. So that's our initial amount. So n of t equals 5. 1, 2, 3, 4, 5. E to the 0.0 499. Oops, that should have been 99. Alright, which isn't 99 minutes, isn't very, again, that's only a little over an hour and a half, right? 1 hour and 39 minutes. How many E. coli bacteria would be there in about an hour and a half? Alright, we type it in. Make sure you're very careful with the numbers. Make sure you put parentheses around that product, and it comes out to 19994. Since we're being estimated, it looks like they rounded up to the nearest whole or big number value. I'd probably round this one up to 2 million bacteria. Minutes. Alright, so again, roughly. It's an estimate, so roughly 2 million bacteria in 99 minutes. I guess you can't read this because my 4s and 9s. It's a 4. Alright, the last question. Determine graphically the elapsed time where there were 20 million bacteria. Alright, so we want to know how long, find the time, find t, when the bacteria, n of t, is 25 million. Alright, how long will it take for the bacteria colony to grow to 25 million? And the reason why we have to solve this graphically is because we haven't talked about logarithms yet. We can't solve this algebraically until we have logarithms. So we only have graphical. So we have to graph the original equation, which was the 500 e raised to the 0.014 times time, which that'll go in there as the x value. So when you graph it, you do have to change the t to x. You're going to have to make your window fairly large because, again, you're going to go up to 3 million or 25 million. So when I'm going to go change my window on my calculator. I'll probably make my x minimum, I'll probably leave -10, but I'll probably change my x max to, I'll start with 500, see if I go from there. My y min, I'll probably leave -10, but my y max, I'm going to go up to 30 million. Make sure, again, 30 million, because I need to go past 25 million. Alright, so that's what we'll have to change your window to. Y1 is going to be my equation. That equation is going to go in y1. Y2 is going to be my 25 million. Alright, graph it on your calculator, and if you do graph it, it should come out where you've adjusted your window. Alright, you will get the exponential growth, so there's n of t, and then you'll get your line, that's the 25 million. And we want to find this moment. What's that time? So where they intersect. So remember how to do this on your calculator. You hit second, trace. You pick intersect, first curve, second curve, and guess. Alright, so usually when I move my cursor as close as I can to that moment, I usually hit, so second, trace, intersect. First curve, second curve, guess. Hit your button. And it comes out 279.43. So 279.43. So I'm just going to round to 279 minutes. Roughly. It'll take a little over 279 minutes to reach 25 million, which again is not a lot of time. It's minutes. Right? And so this bacteria grows really, really fast. Exponentially grows really, really fast. Alright, so we'll stop there. The next video will be looking at applications where you have to set up the exponential equation.